Good morning. Good morning. Namaskar. This is Engineer Suraj Singh speaking from Bharat, India. On this day, July 21, 2021, Wednesday, talk about quality, safety, and engineering. Title being Civil Field Engineering, Quality, AnnexSL, which is structure. Here, engineers role to safety and COVID-19, designs, construction methods, contracts, organizations, communication, coordination, and why we should be behind, quality of concrete standards, and we talk of this general miscellaneous issue every day because certifications that I have and all professionals do have, whatever sort of certificates, educational, academics, or professional, or work related, these certificates are given only when you either pass some examination or you do some job successfully, some project. This means certificate should not be considered only a piece of paper, but a notification that someone is professional, someone is experienced, and someone can be trusted for purpose of achieving quality. This is what these certificates announce. Just like we test using radiography, we test human beings' bones, we test materials, we test everything. These certificates are also like radiography, eyes radiography, mind radiography. These tell that the person has certain competency, but that competency should be proved, which is very important. Quality exists everywhere and should exist, but it should be according to definition that has been considered for whatever requirement. If somebody is qualified engineer, means one is having certain academics of engineering, academic mark, that can be diploma engineering, degree engineering, or post graduation or doctorate, whoever and whatever. It tells that this person has gone through certain test, certain examination, certain vivas and interview, certain projects, and has qualified what was required. Yes, it's not 100% true. It is 50% true, 75% true, because 100% pass is not required in academics. So academics, you can say, is a part qualification, not a full qualification. Means you know something and you do not know something, both conditions stand. Something you know, something you do not know. Do not know doesn't mean that you cannot know. Do not know means you did not study that or you did not worry about that, but you had a chance to pass 50% and get into world of that profession. So you can say that academics is a kind of entry pass. It's a kind of passport to travel to professional world, and that certificate is called diploma or degree or post graduation, or you can say whatever sort of certificate. But that is not competent certificate. That is just entry visa into that domain of engineering, the domain of profession. And it applies not only to engineering, it applies to whole world's qualifications, whole world's education system, in all branches of professions and all other branches. This means academics is only a part quality, not full quality. It's related to education system, it's related to academics. It does not relate to real world of profession. That's true because student and professor has a relation. Professor is guru to student, master to student, teacher to student, trains that student, molds that student from raw to little cooked professional. And when that professional goes to joins field, learns a lot for a couple of years, and if that professional does not learn, that professional can never become professional. In fact, professional means a person who is very well qualified educationally and by experience, trained, well trained, tutorialed, taken responsibility under guidance of seniors, and then gradually becomes independent to, to accept direct responsibility and accountability towards works and towards public. That starts building up of quality professional. Learning never ends, we all know. It goes on, and in particular in professional world, it can never stop. It may be engineering world, medical world, or some other world. It can never stop. It goes on and on. Whether you are in job or you are out of job, whether you are retired or not retired, it goes on and on. It doesn't stop at declaration of retirement or whatsoever. Because professional mind, as old it is, more sharp it is. Professional mind, as it learns, it becomes more and more active. As age develops, it becomes very much powerful. It moves within itself all energies it got. Only difference is maybe energetically a professional is more smart in young age than in old age. But quality factor remains enhancing itself as you grow up in your profession. Quality cannot be defeated, but person is defeated. If I'm not able to produce quality work, I'm not able to deliver quality requirement, and I call myself professional, I cheat myself, I lie to myself. Yes, I can say that I get money, salary or remuneration or fees. That is financial part, that is reward part of my work. But first evaluation of my own capability I have to make as a professional. I have to find solution to my problems. I have to evaluate myself, what level of service I have delivered to this client or this office or to this site. What was my contribution? Was it at a level which it should be, or it was above that level, or it was below that level? This examination I have to conduct myself. Nobody would do it for me, because I am not interested in paper reporting. I am interested in real work reporting. I should know where I made mistake. I should know where I did right. The work shall be accepted. That doesn't matter. The matter is what I did do. Shall I review myself? Shall I edit my work myself even without paper? Or you can say it's a kind of review and learning. We generally call lessons learned. Lessons learned means you have to review your work, you have to know your errors, your mistakes, where did you make mistakes, or where did you stop making mistake and where did you stop making others' mistake. These all acts go on side by side and by end. This is automatic. At end of every day, you think sometime, hey, for a couple of minutes, You remember automatically those instances which were not favorable. Those certainly would come to you to raise questions to you. Why do you not understand us? Maybe sometimes during that self concentration, self analysis, self conflicting time, we get answers because during active time, whole day, I was not able to know that, but when my active cells dropped and those those sleepless cells which raise problems, those come up and tell me, this is what I was. I told you, you didn't listen to me. These cells would tell you, and for sure you will find some solution that day or some other time so that you will do your job correct, but it will take time. And maybe you made errors and you have to correct that one. That's the kind of quality build up. Quality cannot be built up individually in one day or 1 month. It depends on your capability of picking up. It depends on your interest. It depends on your seriousness. If you are serious, you are having one quality, I can say. Serious does not mean that you have very impressive face or very sad face or condoling face. I do not mean that. When I call serious, it is very simple. It doesn't mean you don't laugh. It doesn't mean that you don't enjoy. It doesn't mean that you don't interact with people. It doesn't mean that. You have to do every act. You have to do everything. Seriousness has no link with all these happiness or sadness. Seriousness means continuity. It doesn't mean you put comma or full stop and stop. No. You should enjoy, you should laugh, you should enjoy your work, you should, enjoy working conditions, you should build up working conditions. All that is required in seriousness because seriousness requires energies, and these energies you get through all this activity, extra activity, I can say, interactive, time, dealing with others, and appreciating others' work, helping others, helping self. These are part of seriousness. I'm not saying get angry, no. I'm not saying you be in a state of anguish, no. What I'm saying is one should be serious in work. Serious means do not miss anything. Do not try not to understand what is required. Seriousness means you should have complete information, whatever can be with you. It can be active information, it can be passive information, it can be procedural information, it can be whatever information is possible. You should gather whatever you have, you study that, review that, try to understand that. It won't take many days, it will take just a couple of minutes. If you have a habit to go to every document and understand or use your experience which you had done in past, can you do same or you can improve that? That's what seriousness is. It's like chain of numbers. We say 0, 1, 2, 3 like that, up to 9 or 10 or then up to 100. Let us say, I say 0 to 9. When we say 0 to 9, 0 starts at origin. And I say I go to 9. When I say I start from 0, certainly I cannot jump onto 9 directly. I have to take steps. I have to move in 0 to 1. If I reach 1, I say I have gone through one step. That is the part of seriousness unit. What I say, degree of seriousness. 1 unit I have crossed. That unit means difference between distance 0 to distance 1 or mark 0 to mark 1 is travel distance, and that distance is step in work, seriousness. Same way I go to 2, 3 and up to end. And I can say I have gone to 9 or more. This going from 0 to 9 through 1, 2, 3, 4, 5, 6, 7, 8, and then 9. Successfully moving like this is called process of seriousness. Means the number itself is called serial. Means this serial, this episode, this string you traveled, you covered, is defined seriousness. If you say I could jump directly to 9, well, I think you would collapse because you cannot do that. But just like people walk very fast sometimes during ascending on steps, ascending on waist or slab or stairs, so I jump 1 to 4 to 5 and sometimes you collapse. Your work should be so good that you don't collapse from 0 to 9. You try to understand. Work seriousness and serious work both are reasonable, both are linked, even if you don't realize this, but this applies. That's important part of seriousness. And I should say, just like I mentioned quality SHE, seriousness is a part of quality. With smiling, with charming, with entertaining others, with reading documents, understanding documents, try to know what best way I can do this. It may be design work, it may be construction work, it may be planning work, it may be quality work, it may be safety work. Whatever activities generally we deal with, many activities same time. Activity, when we say it's a part of act. Activities means you have to define yourself what activities you intend to include in whatever plan. It's in your hands. You say, we define in planning or in scheduling, we say it's master schedule or level 1 schedule, where whole project is shown from start day to end day. And maybe very few activities are taken. This can say disciplinary activities are taken, or you can say other heads are taken. Various branches of engineering are taken into that in master schedule, because we have contractually date of start of that project to date of end of that project. So that whole defines all components are included in that, and that's defined as master schedule, or you may say level 1. Likewise, we, for our convenience, for our own understanding, for our own convenience movement, on direct clearance, we use, okay, this is master schedule or level 1. Then we further take level 2, level 3, level 4, likewise. And we take also look ahead, like you can say 3 months look ahead, or 90 days look ahead, or 7 weeks look ahead, or 8 weeks, 9 weeks, or 6 months, or 3 months, or weekly we say, and day to day as well. Though day to day is not separately taken, it's understood every while working, but weekly up to week, 1 week ahead, look ahead, 3 weeks ahead, look ahead, 3 months look ahead. Likewise, we plan it, and that's called seriousness. But it's not simply that you have to plan it like that. Planning is one part of job, scheduling is one part, but your schedule should be that much competent that it gives, it allows, or you can say it digests work days, work time, and that work can be done within that period without any problem, provided you are given required resources, human resources, machine resources, or all other resources you are given. You have to complete that job in that period, or you have to achieve that milestone which was yourself you fixed, which by you, and then that's very important point. So quality says seriousness is its part, activism is its parts, safety is its parts, arrangement of resources is its part, specification is its part. There is nothing that cannot be included within world of quality, because quality means quality of working, quality of system we define, nobody else. In what way I want to construct this working from start to end, I have to define my system to best of my knowledge, best of my information I have. All whatever that project has to do, everything must be covered on that schedule, on that plan, which is very important part in in working on projects, whether it's a design project or it is construction project or some other project. So when we say project, this means very significant work it is. Very significant work means you have to you can say give birth to that project. Give birth means from scratch of that piece of land to making it suitable for purpose of living or using. This whole stage of construction or designs or something else, if you total up all this, it's called project duration. It can be design duration separately, it can be bidding duration separately, it can be construction duration separately, it can be maintenance and operation duration separately. There are so many durations, but ultimately from conception of that project time to starting it to be either occupied or being, you can say, operational. This stage says it's design stage, you may say, or you may say whatever you can say, but this is preparation stage, I can say. Preparation for everything. Design, before that preparation of design of feed, then design, then you can say contracting procedures, or you say how to allow contracting on this, and then construction, and then you can say after construction is over in up to date of completion, then you can say this project is no more project, it comes into status of operational unit. That's also a part of quality. What was that whole quality system you moved through? How much good was safety, health and environment? What was level of ergonomical applications by people, and quality, what do you understand by quality there? That's why I say quality and safety cannot be dispensed with. No way, even if you want, you cannot. Without quality and without safety, health and environment, nothing can work, nothing can move. We have to keep this factor in mind. It's very important factor. Even if you don't want to write quality or write safety, you have to apply these two. You have to adopt these two. Safety is not for permanence, it's for activity. It's for current time. It's called provisional safety, or you may say it's safety of individuals, it's safety of arrangements. That safety I'm talking of. Whatever work our people do, our workers do, they all have a right and have an expectation that our observers, our managers, our organizers shall keep us safe, because everybody has to live. Employment does not mean you kill them. You have to keep them safe, and this is a requirement. And of course, you can say it's a part of quality, or you can say systems quality. System is very important point. If we cannot apply, we cannot realize quality. Is, I think, I do something wrong against myself. I do something wrong against humanity. I do something wrong against my profession, because quality is quality requirement, quality is system. Quality means there is something specific, there is something well defined, procedural it is, and based on that quality we compose nomenclature of items, we control, we produce list of materials, list of manufacturers. There's so many documents in our bidding stage or in contracting stage. So these 2 points. This whole stage of contracting also, whole stage of bidding also, we can say it's a kind of system that we cannot say that it's gone. That system is also very important, because system is system after all. We cannot say no. System is system, and that system has to work. If that system fails to work, everything fails. Once you are an engineer, you may do, may not do, but you are supposed to do, you are required to do work in quality, whether or not that quality is defined. If it is not defined due to whatever reason, then you have to think it according to requirement, according to industrial practice, according to engineering practice, according to what you think is best one. But generally, it's duty of engineers who deal with bidding or designs to define what is required. Design doesn't mean structural design. Design means every documentation, preparation, authentication, all that, because that document when becomes part of bid or part of contract, it becomes very responsible document. Nobody can change it except all involved parties agree. No need changing. Yes, there may be non-clarity that can be taken up. There can be clashes, there can be contradictory statements or contradictory specificational provisions. Those can be reviewed, those can be studied. Nobody minds that. And you cannot say it's not possible for me to get this material delivered or due to some specific reasons I can't do it. You can't say that because you are a contractor. It's your duty to do it. It's your duty prior to filing your bid. You must be sure that this item shall not cause any problem. That's very much necessary. It's a part of scrutiny of your own work. So we can say it's very important that quality changes us. Quality changes our lives. Quality can change whole world. Quality can change complete arrangement. Safety wise. Safety also is a part of quality, but that is, occasional, that is casual, that's temporary. Because you can't expect safety to harm you all the time. It harms you only when you do not care for safety. Safety is an act. It's such an important act that if we don't think of safety, we can lose, we can cost, we can say, we can impact our own people if we don't understand safety. There should be someone who knows what is safety, how it can impact our individuals, workers, and how it can do harm to something else, machines or people or circulation area, whatever. I mean to say, engineers must realize quality facts, and in particular, civil engineers have to change quality aspect of society, or else quality cannot exist. Because when I say quality aspect of society, this means something, not something but everything. Because society moves only when it is organized by someone. It cannot move if you take a group of flock of animals, cows or buffaloes, they will not move according to your requirement. Yes, but you have to control them. And that control factor is very important here. So whatever you can say about safety and quality, these are very important and significant part of humanity. I have no right to spoil my worker. If my worker has no drinking water, must be there. Same way, because water is important in safety, health, both. And whatever is important, quality must be there. We have to understand these points. Quality is dropping everywhere, that's what I can see. It's not in construction, I think in every sector, in every activity of life, it's falling. It's falling character-wise, it's falling physique-wise, it's falling mind-wise. Means those who can lie It's easy for them to lie, but same people find it very difficult to speak truth. Truth or false, true or false, we say. We always consider this whether it's true or it's false. But I would say people have been used to speak false, speak lies. In current scenario, I am finding that people don't find difficult to speak lies, and it has become like a part of system. Young or old, adolescent or kids, all. It's no difficulty for them to speak lies. Interesting? Lying is like, okay, I just speak something and I lie. What shall other part do? Nothing. But what shall also you do? You don't know. You think you have solved problem by lying. In that case, you are wrong. No problem can be solved by lying. You have to face problem to solve a problem. That's very important. And that's part of a system. System's quality to be revised and achieved. Broken system means broken life linked to broken system. And also superficiality, superficial action, superficial approach never pays. Remember, I'm saying pay. Pay doesn't mean salary or money. Pay means circumstances, development. Some problem exists and you have to resolve that problem. It's like that. We have to do our part of job. That's also very important. We can't run away from that. And if we don't do that, we do not do justice to ourselves as individuals or others. We should not forget that we are members of world community. We are members of every pertinent nation's community. We are not community of castes or religions. We are community of intellectuals. Keep apart religion. Keep apart everything. Remove all clothes even and take bath. You are exposed there in bath. Bath tells you what you are. Right? Therefore, quality is quality. You have to understand. It's not quality test only. It's whole system quality. There are thousands of companies, organizations everywhere. This company must realize facts. And if you don't realize facts, I will not go any longer on this because I repeated many number of times. I will go to now what I was talking about. We're talking about radiography operations. Till last talk, these radiography operations were based where I referred to one book, and that was called radiography. That book was radiography. And that's an interesting one. We said that one interesting one. This is about IAEA. Radiation protection and safety in industrial radiography. Radiation protection and safety in industrial radiography. We have gone through this. And I was somewhere, I think, somewhere in on page, I'll leave it there. We've gone through introduction, then objectives of radiation protection and safety, organizational responsibilities regarding regulatory authority, operating organization, industrial radiographer, worker, manufacturer and suppliers, client. We went through exposure devices, gamma radiography sources and containers, X-ray radiography equipment, accelerators, underwater radiography equipment, real-time radiography, pipe crawler equipment, real-time radiography, neutron radiography, designs and use of shielded enclosures. There, enclosures design and use, shielding design for a shielded enclosure, control of exposure in shielded enclosure, operating procedures for shielded enclosures, site aerography procedures, then boundary of control area, shielding, administrative arrangements, monitoring, additional precautions for gamma radiography, additional precautions for X radiography, including use of accelerators, additional precautions for underwater radiography, additional precautions for pipeline crawlers, storage, movement and transport of radiographic sources and exposure devices, storage of source, movement and transport of sources. Emergency response planning says emergency resulting in exposures, emergencies resulting in exposures, emergency planning and preparedness. Emergency resulting in exposures, emergency planning and preparedness, specific emergency procedures and accident notification and reports. So it is, we had gone through this. This was use of instrument to survey an explosive device. Then personal during radiography, during radiography, primary survey objective is to determine that radiographic source has returned to shielded position or that X-ray emission has ceased for each radiographic exposure. Exposure devices have to be approached with probable survey, meter switched on. Exposure devices have to be approached with portable survey meter switched on, since there is possibility of radiographic source being stuck in exposed position of X-ray exposure control having failed. Personal alarm monitors. Radiographers need use personal alarm monitors during whole period that may be exposed to ionizing radiation. Alarm provides a recognizable signal at a suitable dose rate, and we can say radiographers need use personal alarm monitors during whole period they may be exposed to ionizing radiations. Alarm provides a recognizable signal at a suitable dose rate that may be prescribed by regulatory authority. Signals to be visible, visible and quality. Then we have to consider alarm provides a recognizable signal at a suitable dose rate and may be prescribed by regulatory authority. Signal is to be audible, visible or vibratory and recognizable in working environment. These alarms are used in security system. Additional precautions for gamma radiography. We have gone through this also, just repeat. Radionuclide and activity of radiographic source are selected such that dose for all workers is kept alara. Consistent with obtaining adequate diagnostic information. It's possible to do most radiographic work by using iridium-192 with an activity on up to 4.254. Procedure need be rehearsed and only equipment that is specifically manufactured for gamma radiography is to be used. Radiographer needs to be familiar with all of equipment. Procedure need be rehearsed and only equipment that is specifically manufactured for gamma radiography is to be used. Radiographer need be familiar with all equipment, its mode of operation and potential problems. An understanding of source, its appearance and how it is to be exposed is particularly important. Radiography is only to be carried out when exposure container and all necessary equipments are available in good working condition, which include portable survey meters and personal dosimeters, guide rules, Radiography is only to be carried out when exposure container and all necessary equipment are available and in good working condition, which includes portable survey meters and personal dosimeters. Portable survey meters and personal dosimeters, guide tubes, controlled cables and remote control, collimators and local shielding, temporary barriers or tapes, warning notices and signals, emergency kit including remote source handling tools, other ancillary equipment such as clamps and positioning aids. Before leaving site, radiographer carries out a visual examination to ensure that equipment has not been damaged. Exposure container is made ready for transport of Now, following checks are made before use as described in operating procedures. Check exposure container. Check exposure container and exposed ends of cables for damage, wear or dirt. A wear gauge supplied by manufacturer can be used. Check screws and nuts for tightness and screw threads and springs for damage. Confirm that source locking mechanism works properly. Examine end of pigtail for wear damage and proper connection to control cable. Check exposure containers and exposed ends of cables for damage, wear or tear. A wear gauge supplied by manufacturer can be used. Check screws and nuts for tightness and screw threads and springs for damage. Confirm that source locking mechanism works properly. Examine end of pigtails for wear, damage and proper connection to control cables. A wear gauge provided by manufacturer can be used for this purpose. Check connections between exposure container and cable for secure connection. Inspect all cables and guide rules for and against. You can see then there are so many checks left still. Examine end of pigtail for wear, damage and proper connection to control cable. A wear gauge provided by manufacturer can be used for this purpose. Check connections between exposure container and cables for secure connection. Inspect all cables and guide tubes for cuts, breaks, kinks and broken fittings. Cuts, breaks, links and broken fittings. Check warning label and source tag details for legibility. Measure radiation levels close to expense. Inspect all cables, check connections between exposure container and cables for secure connection. Inspect all cables and guide tubes for cuts, breaks, kinks and broken fittings. Check warning labels and source tag details for legibility. Measure radiation levels close to exposure containers surface for compliance with IAEA safety standards. Serial series ST1 and to confirm that safe source is shielded. If discrepancy is noted, that equipment is not to be used until a replacement is provided or repair is done. Additional precautions for X radiography, including use of accelerators. Procedures discussed in this section are applicable to use of all X-ray exposure devices and techniques. This procedure discussed in this section are applicable to use of X-ray exposure devices and techniques, including accelerators and real-time radiography. Selection of X-ray tube voltage is normally closely linked to requirements for quality of radiograph. Procedure discussed in these sections are applicable to use of X-ray exposure devices and techniques, including accelerators and real-time radiography. Selection of X-ray tube voltage is normally closely linked to requirements for quality of radiography. Exposure technique that is used, that is source material and external single wall versus double wall, is selected with regard to good image quality and reduction of dose for all involved. Exposure technique, internal external wall versus double wall, is selected with regard to good image quality and cost. Well, the dose of image quality and reduction of dose for all involved. Now checks that we have to make as described in procedure. Check visible damage on all parts of equipment. Check X-ray tube and all exposed ends of cable for damage, wear, dirt and moisture. Check screws and nuts for tightness and check for visible damage all parts of equipment. Check X-ray tube and all exposed ends of cable for damage, wear, dirt and moisture. Check screws and nuts for tightness and screw threads for damage. Check for visible damage in all parts of equipment. Check X-ray tube and all exposed ends of cable for damage, wear, dirt and moisture. Check screws and nuts for tightness and screw threads for damage. Inspect all cables for cuts, breaks, steel kinks and broken fittings. Check exposure factors, settings for legibility. If discrepancy is noted, equipment is not used until a replacement is provided or repair is made. We read accelerators generate very high energy X-rays which increase potential for overexposures of radiographers. Therefore, higher levels of radiation protections are required in site. Close, you can say higher level of radiation protection is required on site. Dose rate in main beam of an accelerator is high and can range from 4 GV minimum -1. From a mobile accelerator to 50 m GeM min to power -1, 3 GYH -1 from a portable accelerator. This means that dose rate around apparatus is much higher than during conventional X-ray radiography, and so more comprehensive control measures are needed to restrict exposure of people to ionizing radiation. In addition, appropriate portable survey meters are used that respond accurately to pulsed nature of radiation field. Radiation pulse then you can say, in addition, appropriate portable survey meters are used that respond accurately to pulse nature of radiation field, radiation pulse, duration and pulse repetition frequency. Portable survey meters used for conventional gamma and X-ray radiography may not be suitable for use with gamma radiations. Now, portable survey meters used for conventional gamma and X-ray radiography may not be suitable for use with accelerators. Now, additional precautions for underwater radiography. I think this was a little one we went to. Underwater gamma radiography is a specialized technique that requires additional considerations. Appropriate training of divers is necessary before being taken into water. Control mechanism and guide tube are to be connected to exposure container. Connections need be confirmed to be secure and source assembly has to be in secure position. Short line with buoy and emergency location device, for example a strobe light, are to be securely attached to exposure device. This shall aid recovery from water if exposure container is dropped. All equipment such as survey meters to be used underwater. A short line with buoy and emergency location device, for example, a strobe light, are to be securely attached to exposure device. This will aid recovery from water if exposure container is dropped. All equipment such as survey meters to be used underwater needs be specifically suited for this purpose. Additional precautions for pipeline crawlers. This is very important. We studied this, but I'll speak fast because I've already gone through this. General radiation safety requirements for X-ray and gamma exposure devices also apply to pipeline crawlers. With pipeline crawlers, useful beam is equally General radiation safety requirements for X-ray and gamma exposure devices also apply to pipeline crawlers. With pipeline crawlers, useful beam is restricted so that its width is no greater than is necessary for radiograph. When in use, pipeline crawlers are not visible from outside pipe. It's thus essential that suitable warning signals are given. Warning signals of X-ray pipeline crawlers have to operate automatically. It's desirable that gamma pipeline crawlers also operate in this way, where practicable, because unintended movement of control source may inadvertently initiate an unplanned exposure. Says it's desirable that gamma pipeline crawlers also operate in this way, where practicable, because unintended movement of control source may be inadvertently Okay, when in use, pipeline crawlers are not visible from outside pipe. It's thus essential that suitable warning signals are given. Warning signals of X-ray pipeline crawlers have to operate automatically. It is desirable that gamma pipeline crawlers also operate in this way where practicable, because unintended movement of control source may inadvertently initiate an unplanned exposure. Warning signals capable have to be capable of alerting people in vicinity of pipeline crawlers mounted. We can say then warning signals have to be capable of alerting people in vicinity of pipeline crawler under prevailing environmental conditions. Signals are that operate automatically are to be linked with operation of pipeline crawler. Audible signals are attenuated by pipeline, pipe wall, and need be so urgently. Now we'll go to after that. Audible signals are attenuated by pipe wall and need be loud enough to locate pipe crawler accurately. With pipe, klaxons and sirens can be used provided that they can be heard in a noisy environment. Possible supplementary signals outside pipe include visual signal to supplement a audible signal in noisy environment. Visual signal to supplement audible signal in noise environment. A radiation activated warning device manufacture sorry a radiation activated warning device that will indicate position of crawler equipment along pipe. Also, a portable survey meter is used to determine X-ray emission has ceased or that source has returned to shielded position. Now, we say that radiography source, if any, and control source are to be housed in shielded container and together with telltale source should not produce dose rates in excess of 100 USV H-1 on occasion accessible surface of pipeline except during exposure. We'll go to now something else in the radiography source, that is something you can say storage, movement and transport of radiography source and exposure. We did it a lot yesterday. We talked of storage, we talked how it's done, and that's I think also important one that we did. Storage facilities are designed to restrict exposure. Exposure keep radiographic sources, exposure containers and control sources secure against theft or damage and prevent whatever unauthorized persons from carrying out whatever actions which would be dangerous to themselves or to people, to public. Clear warning notices are to be displayed at storage facilities. A suitable storage facility for radiographic sources Exposure containers, control sources, and ancillary requirement is one that provides protection from prevailing environment conditions. Resistance to fire is considered in constructing storage facility in order to minimize loss of shielding and container. Storage facility is to be located at remote distance from a corrosive and explosive hazards. So like that. If outside storage facility is accessible to public, shielding is provided to reduce dose rate in this area to less than 2.5 mu SV/1 or as authorized by regulatory authority. If outside they've gone through this, door is to be kept locked and keys for storage facility and exposure device controls are to be held only by authorized personnel. Physical inventory checks are to be made periodically to confirm location of radiographic source, exposure containers and control source, movement and transport of sources. When gamma exposure device and sources are to be moved around a work sense, they are not to be removed from storage facility until they are ready to be used. Sources are to be moved only in appropriate containers such as transport packages which are locked correctly and keys of which are removed. A vehicle or trolley is best used to move containers under these circumstances. Containers are secured to vehicle or trolley and are kept under surveillance for duration of movement on work site. Requirements for transportation of radioactive materials are published in IAEA safety standards. You can refer to that. All right. You can read this meanwhile, and I'll be back after some time. Right. As usual, I'm going to stretch something, and these some pages left will do. Take care of this. Sorry. So we continue as such. We continue our work. Sorry for disturbance. All transport, you can say, here, we will take it. All transport of radioactive sources should comply with containment, labeling and documentation requirements and whatever existing national legislation. Provisions should be established to ensure compliance through appointment of regulatory authority for transport of radioactive materials. Regulatory authority sets up and executes a program for monitoring, design, manufacturing, testing, inspection and maintenance quality assurance of packages. It says regulatory authority sets up and executes a program for monitoring, design, manufacturing, testing, inspection and maintenance quality assurance of packages. Industrial radiographic exposure containers should satisfy requirements of type A or type B packages for transport. Summary of requirements for this transport of packages is included in Schedule 9 and 10 of IAEA Safety Series. Operating organizations are often consignors, shippers of exposure devices and from temporary works sites, and therefore responsibilities laid down for consignors are also applicable. They ensure that all packages are properly prepared for transport, including securing all required plugs, caps and locks before transport. All conditions of whatever applicable authorization for packages must be met. Gamma exposure devices are frequently transported by road by operating organization. Drivers and vehicles must comply with applicable requirements of national and international roads. These requirements prescribe necessary safety equipments on vehicles, placarding, transport documentation and training of drivers. In event of a transport accident, vehicle driver, local emergency services or whatever other person discovering accident shall contact package consignor and or consignee who are identified on transport documentation. Both organizations are to be fully aware of emergency plans and provide or call for practical advice and assistance. IAEA Safety Series 87 gives guidance and recommendations for dealing with transport vehicles, transport accidents and useful for preparation of transport emergency plans. Emergency response planning. Accidents have occurred in industrial radiography resulting in workers and members of public being exposed to radiation and other health and safety hazards. Typical situations which have led to radiological hazards include loss of control of source or exposure device, damage to source or exposure device and direct contact with source. So it says that accidents have occurred in industrial radiography resulting in workers and members of public being exposed to radiation and other health and safety hazards. Typical situations which have led to radiological hazard include loss of control of source or exposure device, damage to source or exposure device and direct contact with source. Emergency resulting in exposures. Experience and analysis of kind described have shown that most likely events involving gamma exposure devices with greatest potential for significant radiation exposure to workers and general public content, failure to retract source and failure to perform. Failure to retract source and failure to perform an adequate radiation monitoring survey. A source stuck in guide tube, collimator or near entrance to exposure container, source disconnection from camera cable, an exposure device stuck in exposed position, such as shutter remaining open, theft of exposure device or source assembly, malfunction or deliberate defeat of safety control system, contamination due to leaking or damaged source. Most serious exposures occur when a worker remains next to it or physically handles unshielded source assembly, when source assembly is mishandled, or when it is in a possession of members of general public. Dose rates are high enough to cause localized overexposure in matter of seconds or minutes and can result in severe injury and even death. Most likely event involving X-ray exposure devices with potential for significant exposure to workers are an automatic exposure timer. An automatic exposure timer fails to terminate an exposure, resulting in tube assembly remaining energized. Tube assembly is energized unintentionally. Operator neglects to terminate exposure and fails to perform an adequate radiation monitoring survey before manipulating tube assembly. There is damaged, faulty or deliberately defeated safety equipment and systems, such as malfunctioning interlocks. Physical damage affects shielding or filtration. Emergency planning and preparedness. Emergency planning and preparedness has four major components: assessment of hazards, acquisition of emergency equipment, development of written procedures, and training to deal with emergency situations, including training in handling of emergency equipment in following written procedure. Basic obligations, responsibilities, and requirements for emergency situations are established in Safety Series number 15. Advice and guidance on developing and implementing emergency plans are provided in the Safety Series number 91, and a step-by-step method for developing integrated user, local, and national emergency response capability is set up in IEATE Tech Document 953. Accidents in radiographic may result in deterministic health effects due to loss of shielding or inadequate access control. They may also result in localized contamination from lost or stolen sources. Emergency planning starts with assessment of hazards, which involves analysis of normal conditions, how they may change during an emergency, possible types of accidents and their possible magnitudes and consequences on site and off-site. Next step is to determine and assign role and responsibilities of each individual group of organization involved in emergency preparedness and response. Plan describes role and responsibilities of all involved in response and also contains a brief description of possible accidents and a concept of operation. Responsibility for preparing plan lies with operating organization. For preparing plan lies with operating organization. Emergency procedures are to be written to deal with each foreseeable emergency. These have to be concise, easily followed instructions describing what factors are necessary indicative of a situation requiring emergency action, specifying immediate action to be taken to minimize radiation exposure or to persons in vicinity of source and necessity for planning a course of action. Procedures are to include names and telephone numbers of people identified in emergency response, for example, radiation protection officer, regulatory authority, medical doctor, manufacturer, emergency services, qualified expert, and other parties as applicable. Operating organization is to develop capabilities needed to implement emergency plan. This entails training of staff to deal with emergency situations, including training in handling of emergency equipment and in following written procedures. Once a response capability has been developed, drills and exercises need be conducted periodically. These drills and exercises provide training but also test and validate plan, procedures and training of emergency personnel. Following drills and exercises, deficiencies are identified and corrected. Periodic assessment includes verifying that all names and telephone numbers in emergency procedures are still accurate and up to date, and that emergency equipment is adequate. Operating organization is also responsible for liaison with emergency services, police, fire and medical, qualified experts and other bodies that are designated in procedures. Purpose of this liaison is to ensure that all parties understand hazards and are aware of requirements of emergency procedure and responsibilities for action. In event of an accident, its coordinated response of emergency services and other bodies, as well as inform regulatory authority. In an emergency response, generic response scheme designates responsible person under three specific titles: response initiator, emergency manager, and radiological assessor. Response initiator, first responder on scene. This is first who initiates response and performs immediate action to mitigate accident. This is a response initiator. Emergency manager, FEM, emergency manager EM is in charge of overall emergency response and manages, organizes priorities and protection of public and emergency workers. EM ensures that appropriate resources have been activated. Radiological assessor. Radiological assessor is responsible for radiation surveys, dose assessment, contamination control, radiation protection support to emergency workers, and formulation of protective action recommendation. Radiological assessor also initiates and in many cases carries out source recovery, clean up and decontamination. This position is normally held by radiation protection officer or a hired qualified expert. In industrial radiography, response initiator is most likely to be a radiographer himself, while emergency manager may be operating organization manager or a designated senior staff member. In case of a lost source, emergency manager may be an appointed member of local government. EM is designated to be primary spokesperson for media. In small organizations, radiographer may be RPO and EM at same time. In emergency equipment, the emergency equipment has to be obtained to adequately respond to an emergency. It's suggested that following minimum resources be made available by operating organization. Radiation survey instruments. High range gamma survey instrument measuring dose rates up to several sieverts per hour. Low range survey instrument, contamination monitor or probe, check source for low range survey instruments. Personal protective equipment, self-reading dosimeters for each team member, permanent dosimeters for each team member, protective overalls, overshoes and gloves, gloves, first aid kit, communication equipment, portable radio communications, supplies, appropriate shielding sufficient to attenuate Radiation significantly, for example, at least 2 bags of lead shot, that is 2 kg each for 192 IR and 10 kg each for 60 CO, cobalt 60. Tongs at least 1.5 meter long, suitable for safety handling, source assembly, a shielded container, appropriate hand tools, radiation warning labels and signs, plastic for preventing contamination of instruments, logbook, supporting documents, equipment operation manuals, response coordination procedure, procedures for conducting monitoring, procedures for personal radiation protection, specific emergency procedures. Most gamma radiographic sources, most gamma radiography incidents involve a failure of radiographic source to return to shielded position. In dealing with these incidents, special equipment is necessary, and a first priority is protection of persons. Most gamma radiography incidents involve a failure of radiographic source to return to shielded position. In dealing with these incidents, special equipment is necessary, and first priority is protection of persons. In what follows, practical guidance is provided for remedial actions. Application of each procedure shall depend on the specific details of each case. Although steps are listed in general sequence in which they are to be performed, it's possible that sequence may need be adopted at a time of response. Operating organization authorizes and trains different workers to implement different remedial actions. Within emergency plans, individual workers are only to implement parts of emergency plan for which they have been authorized and trained, and for which they have to appropriate equipment. For guidance, steps are classified according to designated offenses, responsibilities, that is radiographer, RPO, or emergency manager. Radiographer, response initiator. Radiographer recognizes that an abnormal situation has occurred which might constitute an emergency. Move away from exposed source and remain calm. Measure radiation dose rates. Establish control area barriers based on dose rate limit requirements. Prevent access to new control area. Do not leave control area unattended. Inform RPO of operating organization and client and seek assistance. Radiant protection officer. Radiation protection officer. Plan a course of action based on previously established emergency procedures, taking into account doses that may be received by this course of action, and keeping an LRA as low as possible, as low as reasonably acceptable. Rehearse planned course of actions. Rehearse planned course of actions before entering control area. Implement planned course of action to extent the training equipment. Training equipment authorization allowed. Under no circumstances should source be allowed to come into contact with hands or other parts of body. If planned course of action is unsuccessful, leave control area and consider next course of action while continuing surveillance of control area. Call technical assistance if needed from qualified experts to manufacturers. Notify regulator authority as possible. when notify regulatory authority is required. When emergency is resolved, reconstruct accident, assess doses received and prepare a report. Send out personal dosimeters for exposure assessment. Send damaged, send damaged and send out personal dosimeter for exposure assessment. Send damaged or malfunctioning. Now you can say send damaged and malfunctioning equipment to manufacturer. Let's say if planned course of action is unsuccessful, leave the control area. All right, notify regulatory authority. If I say I can send out personal dosimeters for exposure assessment, send damaged or malfunctioning equipment to manufacturer or qualified expert for a detailed inspection before reviews. So we have gone through this, right? Now missing or stolen sources or exposure devices. Missing or stolen sources or exposure devices. A missing or stolen exposure device containing radiographic source can be a significant hazard if members of public who are not aware of danger of radiation find it. First priority in this type of accident shall be to identify location of source as well as all people who may have unknowingly handled it. Information on type of source, its activity and other physical and chemical characteristics shall be essential in assessing its potential hazards for people or public. We can now see the first priority in this type of accident shall be to identify location of source as well as all people who may have unknowingly handled it. Information on type of source, its activity and other physical and chemical characteristics shall be essential in assessing its potential hazard for public. Efforts to take source would normally start at its last known location. Investigative work is conducted to retrace sequence of events, reports from medical community on possible contaminated or overexposed victims, surveys by RPO you can say reports from medical characters will be essential in assessing its potential hazards for people. The efforts to track source would normally start at its last known location. Investigative work is conducted to retrace sequence of events, reports from medical community on possible contaminated or overexposed victims, surveys by RPO, and investigation by police are all possible sources of information on sources whatsoever. So we can say that searching for lost source with radiation monitoring equipment is effective for a high activity unshielded high energy gamma source such as industrial radiography sources. Instruments with large sodium iodide. Then you can say searching for a low source with radiation monitoring equipment is effective for a high activity, unshielded, high energy gamma source such as industrial radiography sources. Instruments with large sodium iodide detectors are are able to detect such unshielded sources at distance of up to a few hundred meters. So it says searching for a lost source with radiation monitoring equipment is effective for a high activity, unshielded, high energy gamma source such as industrial radiography sources. Instruments with large sodium iodide detectors are able to detect such unshielded sources at distances of up to a few hundred meters. If source is missing, following items give practical guidance for remedial actions. Steps are classified according to designated officer. Then you can say if a source is missing, following items give practical guidance for remedial actions. Steps are classified according to designated officer, that is radiographer, RP or emergency manager. Radiographer response initiator initiate a search immediately using a radiation monitoring instrument. If source has been lost in transit, retrace plant route, take by device and source and search visually and with aid of radiation monitoring instruments. If it's concluded that source is lost or stolen, notify RPO and or regulatory authority immediately. Radiation protection officer initiate emergency plan. When source is found, inspect it for evidence of tampering and monitor it for shielding damage. Perform a wipe test. If test results are satisfactory, perform wipe test for leakage of radioactive material. If test results are satisfactory, resources return to manufacturer or qualified expert for detailed testing. If test results are not satisfactory, initiate emergency plan. Emergency manager communicate with hospitals, media and public when necessary to help locate missing source and if necessary warn of potential health effects. Rare events have been reported involving leakage or damaged sources. If indications are that source is damaged, see following items. Radiographer immediately inform RPO who may require assistance from a qualified expert, manufacturer or regulatory authority if instructed to do so. And wearing protective clothing, gloves, place device and ancillary equipment in strong plastic bags. Place device and ancillary equipment in strong plastic bags to prevent the spread of contamination. Place protective clothing in a plastic bag and seal all bags used and kept in bags in a control area. X-ray equipment. In an abnormal situation, moving an X-ray tube assembly, assume that it constitutes an emergency, so that following steps are to be taken. Radiographer recognize that an abnormal situation has occurred which might constitute recognize that an abnormal situation has occurred which might constitute an emergency, turn off electrical power, perform a radiation survey to confirm that tube is de-energized, do not move device until details such as position, beam direction, Exposure settings, tube voltage, current and time are recorded. Inform RPO on what has happened. Do not use device until it is examined and prepared as necessary by a qualified expert or manufacturer. Radiation protection officer. Reconstruct the accident, assess doses received and prepare a report. Send out personal dosimeter for exposure assessment. Accident notification and report. I'll do it. Just hold on, please. where accident where accident notification is required, it is important that information provided is complete and accurate, and that notification is made as soon as possible. Accidents are reported to regulatory authority in accordance with regulatory requirements or authorizations and time scales for notification, depending on severity of accident. Major radiological consequences can be avoided if actions are initiated quickly for those accidents that have broader implications for workers, public and environment. Notifications are to be followed up by a written accident report which includes a description of accident, methods used to render source of radiation safe, assessment of exposures, workers, emergency services, personal members of public, cause of accident and corrective actions. Accident reports are to be evaluated by regulatory authority in conjunction with operating organization and manufacturer or supplier as appropriate. Lessons learned from accident have to be communicated to all involved, and whatever necessary improvements to enhance safety carried out. I repeat this concluding paragraph. Accidents notification and report. Where accident notification is required, it's important that information provided is complete and accurate, and that notification is made as soon as possible. Accidents are reported to regulatory authority in accordance with regulatory requirements or authorizations and time scales for notification. Depending on severity of accident, major radiological consequences can be avoided if actions are initiated quickly for those accidents that have broader implications for workers, public and environment. Notifications are to be followed up by a written accident report which includes a description of accident, method used to render source of radiation safe, assessments of exposures, workers, emergency services, personal members of public, cause of accident and corrective actions. Accident reports are to be evaluated by regulatory authority in conjunction with operating organization and manufacturer or suppliers as appropriate. Lessons learned from accident have to be communicated to all individuals, all involved, and whatever necessary or whoever necessary improvements to enhance safety carried out. This has been safety report. Just forward you can see, or forward so we can understand what I have gone through. Use of ionizing radiations, particularly in medicine industry, is growing throughout the world with further expansion likely as technical developments results from research. One of longest established application of ionizing radiation is industrial radiography, which uses both X radiations and gamma radiations to investigate integrity of equipment and structures. Industrial radiography is widespread in almost all member states. It's indispensable to quality assurance requirements in modern engineering practices and feature in work of multinational companies and small business alike. Industrial radiography is extremely versatile. Equipment required is relatively inexpensive and simple to inoperate. It may be highly portable and capable of being operated by a single worker in a wide range of different conditions, such as at remote construction sites, offshore locations, and cross-country pipelines, as well as in complex fabrication facilities. Associated hazards demand that safe working practices be developed in order to minimize potential exposure of radiographers and whatever other persons who may be in vicinity of work. Use of shielded enclosures, fixed facilities with effective safety devices significantly reduce whatever radiations exposures arising from work. Demands and rewards of industrial radiography, ready, ready availability of essential equipment, wide range of working conditions, and fact that techniques employed usually involved in routine manipulation and exposure of powerful gamma emitting sources and X-ray machines have all been identified as contributing to likelihood of accidents. Even in member states with highly developed regulatory infrastructures, industrial radiographers on average receive radiations doses that exceed those of other occupationally exposed workers. And individuals, industrial radiographers are most likely group of workers to receive doses approaching relevant dose limits. Radiation protection safety in industrial radiography is thus of great importance in both developed and developing countries. The safety report summarizes good and current state of art practices in industrial radiography and provides technical advice on radiation protection and safety. It contains information of regulatory authorities, operating organizations, workers, equipment manufacturers, and client organizations with an intention of explaining their responsibilities and means to enhance radiation protection and safety in industrial radiography. So this was, chapters we discussed in this. For your information, this is very important preliminary information for engineers. So we should be very much, we should have certain input about this. This input is a good one for general knowledge. Something we can say fundamentally move forward. Now we'll go to our paper, our statement that's more or less important to be understood. Now we use one dose rates within range. Dose rates was mu SVH minus 1 2.5 ohm, and this is full rate, full scale at dose rates up to 100 m SVH minus 1. Let us see what's that. Dose rates. What is dose rate? We'll see dose rates, capitalization dose rates. Let's go to someone and see what's dose rates. this one here. I'll give this one. So it's actually this is a paper here. You can say USNRC, United States Nuclear Regulatory Commission. United States Nuclear Regulatory Commission. This is United States Nuclear Regulatory Commission, protecting people and environment, measuring radiations. There are 4 different but interrelated units for measuring radioactivity exposure: absorbed, dose, and dose equivalent. This can be remembered by memory, by mnemonic READ. Mnemonic READ is a procedure just to say, if you read as follows with both common British, namely CI, British CI, and international metric EQ, BQ unit, and BUC. So this is United radioactivity. This is measuring radiation. READ. Radioactivity, exposure, absorbed, dose equivalent. Stands for exposure. E stands for exposure. E stands for absorbed. D stands for dose equivalent. Radioactivity refers to amount of ionizing radiation. Radioactivity refers to amount of ionizing radiation released by a material. Ionizing radiation released by a material, whether it emits alpha or beta particles, gamma rays, X-rays, or neutrons. This is whether it emits alpha or beta particles, gamma rays, X-rays, or neutrons. A quantity of radioactive material is expressed in terms of its radioactivity, that is reading RM. Basic reference glossary radioactivity HTML. This site, if you refer, you'll get this. Or simply its activity, which represents how many atoms. You can say radioactivity, which represents how many atoms in material decay in a given time period. Units of measure for radioactivity are Curie. Units of measure for radioactivity are Curie, Curie, Ci, and becquerel, Curie and becquerel, BQ, CiBQ. So we have to understand this point. Definition of radioactivity means amount of ionizing radiation released by material. Radioactivity refers to amount of ionizing radiations released by a material, whether it emits alpha or beta particle, gamma rays, X-rays or neutrons. A quantity of radioactive material is expressed in terms of its radioactivity, which represents how many atoms in material decay in a given time period. How many atoms in material decay represents how many means representation of how many atoms in material decay in given time period. The units of measure for radioactivity are Curie, Ci or BQ, becquerel. Exposure. Exposure describes amount of radiation traveling through air. Many radiation monitors measure exposure. Many radiation monitors measure exposure. Units for exposure are Roentgen R, and Coulomb kilogram, C per kilogram, Coulomb kilogram. So radioactivity is Curie and we are back to this exposure. This is Coulomb per kilogram or R, Roentgen. Absorbed. Dose describes amount of radiation absorbed by an object or person. That is amount of energy that radioactive sources deposit in materials. Amount of energy that radioactive sources deposit in materials through which they pass. Units for absorbed dose are radiation absorbed dose and Gray. Radiation absorbed dose is RAD and Gray GY. This is absorption. Dose equivalent or effective dose combines amount of radiation absorbed and medical effects of that type of radiation. For beta and gamma radiation, dose equivalent is same as absorbed dose. By contrast, dose equivalent is larger than absorbed dose. For alpha and neutron radiation, by contrast, dose equivalent is larger than absorbed dose for alpha and neutron radiation. Because these types of radiations are more damaging to human body. By contrast, dose equivalent is larger than absorbed dose for alpha and neutron radiation. Because these types of radiations are more damaging to human body. Units for dose equivalent are Roentgen equivalent man, and Sieverts SV, Roentgen and Sieverts SV, and biological dose equivalent are commonly measured in 1/1000th of a REM. known as millirem or amrem, REM, that is Roentgen equivalent, man, REM, and biological dose equivalent are commonly measured in 1 over 1000 of a REM, known as millirem. For practical purposes, 1 hour exposure is equal to 1 rad absorbed dose. One rad absorbed dose equal to 1 ram or 1000 mram dose equivalent. Note that measure given CI tells radioactivity of a substance, while a measure in REM tells amount of energy that a radioactive source deposits in living tissue. For example, a person who received a dose equivalent to 1 rem from one of following activities: 3 days of living in Atlanta, 3 days of living in Atlanta, any dose, 2 days of living in Denver, 1 year of watching television on average, 1 year of wearing a watch with luminous dial, 1 coast-to-coast airline flight, 1 year living next door to normally operating nuclear power plant. Got it? It says, note that measure given in CI tells radioactivity of a substance, while a measure in REM tells amount of energy that a radioactive source deposits in living tissue. For example, a person would receive a dose equivalent to 1 mrem from whatever one of following activities: 3 days of living in Atlanta, that is 2 days of living in Denver, 1 year of watching television, 1 year of wearing a watch with luminous dial, coast-to-coast airline flight, and if 1 year living next door to normally operating nuclear power station. This important page I tried to show to you because this is very important from understanding point of view. If you do not understand this, we cannot understand, what you can say, anything. So I now, we have got what is SV. In fact, I am not interested in SV. We have units here, read units. Read means radioactivity, E means exposure, A means absorbed, and D means dose equivalent. In this we say units of radioactivity are Curie, CI, or becquerel, PQ. This is radioactivity units. Exposure unit are R, that is Roentgen, and coulomb per kilogram, that is C. Absorbed doses are, you can say, rad, that is absorbed doses rad, and gray, GY, and dose equivalent is air, and that is SV. You can say units for dose equivalent, that is Sieverth, SV, and biological dose equivalent, commonly measured 1 over 1000 of REM. For practical purposes, this is equation, so we understand basics behind this. Now we go to, say, radiography. Discuss now PDF. We'll close this and we'll take this one. And before this, if we can find something else here, let us see. Measure radiations, and now radiation basics. Radiation basics, let us say radiation basics also we see. Radiation is energy given off by matter in forms of rays. Let us see if we can get something out of this. This is better if we take this just for information purpose. I'll take this one as well. Let us understand radiation first of all, because it is very important from every point of view. It's also from USNRC Radiation Basics, and this is radiation. This URL not to read. Radiation is energy. Radiation is energy. Radiation is energy. Energy you can see given by, let me just blow it up if I can do it. Okay, radiation is energy given off by matter in form of rays. Radiation is energy given off by matter in form of rays or high-speed particles. High-speed particles, rays. All matter is composed of atoms. All matter are composed of matters. Every matter is composed of atoms. Atoms are made up of various parts. Nucleus contains minute particles. Nucleus contains minute particles called protons and neutrons, and atom's outer shell contains other particles called electrons. I repeat, every matter is composed of atoms. Atoms are made up of various parts. Nucleus contains minute particles called protons and neutrons, and atom's outer shell contains other particles called electrons. Nucleus carries a positive electrical charge while electrons carry a negative electrical charge. These forces within atom work towards a strong, stable balance by getting rid of excess atomic energy. These forces within atom work towards a strong, stable balance. These forces within atom work towards a strong, stable balance by getting rid of excess atomic energy. In that process, unstable nuclei may emit a quantity of energy. Unstable nuclei emit a quantity of energy, and this spontaneous emission is what we call radiation. For you can see other particles also, physical forms of radiation, radioactive decay, nuclear fission, ionizing radiation, alpha particles, beta particles, gamma rays and X-rays, neutrons, etc. We'll see physical form of radiation. As previously indicated, matter gives off energy, that is radiation, in two basic physical forms. One form is radiation is pure. One form of radiation is pure energy with no weight. One form of radiation is pure energy with no weight. This form of radiation known as electromagnetic radiation. One form of radiation is pure energy with no weight. This form of radiation known as electromagnetic radiation is like vibrating or pulsating rays or waves of electrical and magnetic energy. Familiar types of electromagnetic radiation include sunlight. Familiar types of electromagnetic radiation include sunlight, X-rays, radar, and radio waves. Other form of radiation, known as particle radiation, is tiny, fast-moving particles that have both energy and mass, or you can say weight. This less familiar form of radiation includes alpha particles, beta particles, and neutrons, as explained below. Radioactive decay. As previously indicated, as previously indicated, large unstable atoms become more stable. Large unstable atoms become more stable by emitting radiation to get rid of excess atomic energy. This radiation can be emitted in form of positively charged alpha particles, negatively charged beta particles, positively charged alpha particles, negatively charged beta particles, gamma rays, neutrons, that is gamma rays, X-rays, neutron, as explained below. Through this process called radioactive decay, radioisotopes lose their radioactivity over time. Radioisotopes lose their radioactivity over time. Through this process called radioactive decay, radioisotopes lose their radioactivity over time. This gradual loss of radioactivity is measured in half-lives. Essentially, a half-life of a radioactive material is time it takes 1/2 of atoms of a radioisotopes to decay by emitting radiation. This time can range from fractions of a second fraction of a second, that's for radon, to millions of years, that is for thorium-232. When radioisotopes are used in medicine or industry, it's vital to know how rapidly they lose their radioactivity in order to know precise amount of radioisotopes that is available for medical procedure or industrial use. Nuclear fission. In some elements, nucleus can split as a result of absorbing an additional neutron. In some elements, nucleus can split as a result of absorbing an additional neutron through a process called nuclear fission. Nucleus can split as a result of absorbing an additional neutron through a process called nuclear fission. Such elements are called fissile materials. One particularly notable fissile material is uranium-235. This is isotope that is used as fuel in commercial nuclear power plants. When a nucleus fissions, it causes three important events that results in release of energy. Specifically, these events are release of radiation, release of neutrons, usually 2 or 3, and formation of 2 new nuclei. Ionizing radiation. Radiation can be either ionizing or non-ionizing, depending on how it affects matter. Non-ionizing radiation includes visible light. Non-ionizing radiation includes visible light, heat, radar, microwaves, and radio waves. This type of radiation deposits energy in materials through which it passes, but it does not have sufficient energy to break molecular bonds or remove electrons from atoms. Non-ionized. By contrast, ionizing radiation such as X-rays and cosmic rays is more energetic than non-ionizing radiations. Ionizing radiation such as X-rays and cosmic rays is more energetic than ionizing radiation. Consequently, when ionizing radiation passes through material, it deposits enough energy to break molecular bonds and displace or remove electrons from atoms. This electron displacement creates two electrically charged particles, ions, which may cause changes in living cells of plants, animals, and people. Ionizing radiation has a number of beneficial uses. For example, we use ionizing radiation in smoke detectors and to treat cancer or sterilize medical equipment. We use ionizing radiation in smoke detectors and to treat cancer or sterilize medical equipment. Nonetheless, ionizing radiation is potentially harmful if not used correctly. Consequently, United States Nuclear Regulatory Commission (NRC) strictly regulates commercial and institutional uses of nuclear materials, including following 5 major types of ionizing radiations. Alpha. See, there are 4 limitations, and that is paper, skin, wood, cement. Alpha up to paper, beta up to skin, medical X-rays up to cement, gamma to cement, neutron crossing that. Alpha particles, beta particles, gamma rays and X-rays and neutrons. Let us see what is that. Alpha particles. Alpha particles are charged particles which are emitted from naturally occurring materials such as uranium, thorium, and radium. Alpha particles are charged particles which are emitted from naturally occurring materials, uranium, thorium, and radium, and man-made elements such as plutonium and americium. Plutonium and americium. These alpha emitters are primarily used in very small amounts in items such as smoke detectors. In general, alpha particles have a very limited ability to penetrate other materials. In other words, these particles of ionizing radiation can be blocked by a sheet of paper. In general, alpha particles have very limited ability to penetrate other materials. In other words, these particles of ionizing radiation can be blocked by a sheet of paper, skin, or even a few inches of air. Nonetheless, materials that emit alpha particles are potentially dangerous if they are inhaled or swallowed, but external exposure generally doesn't pose a danger. Beta particles. Beta particles, which are similar to electrons, are emitted from naturally occurring materials such as strontium. Strontium 90. Such beta emitters are used in medical applications such as treating eye disease. Beta particles, which are similar to electrons, are emitted from naturally occurring materials. Such as strontium 90. Such beta emitters are used in medical applications such as treating eye disease. In general, beta particles are lighter than alpha particles. Beta particles are lighter than alpha particles, and they generally have a greater ability to penetrate other materials. As a result, these particles can travel a few feet in air and can penetrate skin. Nonetheless, a thin sheet of metal or plastic or a block of wood can stop beta particle. Gamma rays and X-rays. Gamma rays and X-rays. Gamma rays and X-rays consist of high energy waves. High energy waves that can travel great distances at speed of light and generally have a great ability to penetrate other materials. For that reason, gamma rays such as from cobalt 60 are often used in medical applications to treat cancer and sterilize medical instruments. Similarly, X-rays are typically used to provide static images of body parts such as teeth and bones, and are also used in industry to find defects in welds. Despite their ability to penetrate other materials, in general, neither gamma rays nor X-rays have ability to make anything radioactive. Several feet of concrete or a few inches of dense material such as lead are able to block these types of radiations. Several feet of concrete or a few inches of dense material such as lead are able to block these types of radiations. Neutrons. Neutrons are high-speed nuclear particles. Neutrons are high-speed nuclear particles that have an exceptional ability to penetrate other materials. Of 5 types of ionizing radiation discussed here, neutrons are only one that can make objects radioactive. This process, called neutron activation, produces many of radioactive sources that are used in medical, academics, and industrial applications, including oil exploration. Because of their exceptional ability to penetrate other materials, neutrons can travel great distances in air and require very thick hydrogen containing materials such as concrete or water. Neutrons can travel great distances in air and require very thick hydrogen containing materials such as concrete or water to block them. However, neutron radiation primarily occurs inside a nuclear reactor, where many feet of water provide effective shielding. So this is what I said is important for us to understand what we thought is true and we have done it. Now we go to other, again to, let's go here, see what's next one. That's radiation basics, and now information of radiation workers, high radiation doses, radiation exposure. Now we'll see information of radiation. Now measuring or detection radiation. First of all, detecting radiation. Let's say detecting, oh no, what's that? Detecting radiation. Let's see what says. I print out. Detecting radiation is another part of this we have to see. But this is also from United States Nuclear Regulatory Commission. Detecting radiation, although many radioactive materials are silver colored, although many radioactive materials are silver colored, metallic solids, I'll put this radiography off now better. Although many radioactive materials are silver colored, metallic solids in their pure state, they can vary in color and exist in different physical states. So it says, although many radioactive materials are silver colored, metallic solids in their pure state, they can vary in color and exist in different physical states, including liquids and gases. They are also physically indistinguishable. From other known radioactive metals. In addition, ionizing radiation is not detectable by one's senses. It cannot be seen, heard, smelled, tasted, or felt. For these reasons, simple visual inspection is insufficient to identify radioactive materials, and radiation sources can be virtually impossible to recognize without special markings. To address these problems, scientists have developed following four major types of instruments to detect and identify radioactive materials and ionizing radiation. Personal radiation detector, PRD, handheld survey meter, radiation isotope identification device, RIID, radiation portal monitor, RPM. So let us repeat: personal radiation detector, PRD, handheld survey meter, radiation isotope identification device, radiation portal monitor, RPM. Personal radiation detector, PRD. PRD is variable gamma. PRD is a variable gamma or neutron radiation detector, approximately size of a pager. When exposed to elevated radiation levels, device alarms with flashing lights, tones, and or vibrations. Most PRD, personal radiation detector, numerically display detected radiation intensity on a scale 0 to 9, and thus can be used to locate a radiation source. However, they typically are not as sensitive as handheld survey meters and cannot identify type of radioactive source. Handheld survey meters, as name implies, Survey meter is a handheld radiation detector which typically measures amount of radiation present and provides this information on a numerical display in units of counts per minute, counts per second, or microengen, microengen, mu r, microengen, or microrem, mu rem, per hour. Most of these devices detect beta and gamma radiation only. However, some models can detect alpha, beta, gamma, and or neutron radiation emitted from radioactive materials. Tele one particular material known as teledetector is specifically designed to detect gamma and X-ray radiations. Named for its telescoping ability, this device can be extended to about 4 meters to measure very high dose rates without subjecting user to unnecessary exposure. In addition, these devices typically have ability to measure dose rates ranging from 0 to 1000 rad per hour. Radiation isotope teledetector. This is teledetector. Radiation isotopes identified on device. A RIID is a radiation detector with ability to analyze energy spectrum of radiation. In order to identify specific radioactive material, radionuclide, this is emitting radiation. In addition, these devices can be used as survey instruments to locate radioactive material. Radiation portal monitor. A RPM is a large pass-through radiation monitor, or portal for personal vehicles, container boxes, or trains. Typically, these devices consist of two pillars containing radiation detectors, which are remotely monitored from a display panel. These monitors alarm to indicate presence of radioactive materials, including low radiation materials like uranium. We'll go to now another one. Information for radiation workers. Let us see how does it work. Information for information for radiation workers. The US Nuclear Regulatory Commission has a wealth of information available for those who work with and around nuclear materials, as illustrated by following examples. Training requirements for radiation. Training requirements for radiation workers. Dose limits for radiation workers. Radiation worker dose history database. How radiation workers and licenses can obtain dose histories from NRC. Training requirements for radiation workers. Title 10, Part 19 of Code of Federal Regulations. Notices, instructions and reports to workers. Inspection and investigations provide instructions to radiation workers, specifically 10 CFR Part 19 requires that all individuals who in course of their employment are likely to receive a dose of more than 100 milligram in a year must receive adequate training to protect themselves against radiation. Also, these individuals have right to know amount of radiation to which they have been exposed. In addition, radiation workers have right to ask NRC to conduct an inspection if they believe their working environment has safety problems. Dose limits for radiation workers. Standards for protection against radiation establishes dose limits for radiation workers. Although limits vary depending on affected part of body, annual total effective dose equivalent TEDE for whole body is 5000 mrem. Radiation workers dose history database. Among NRC licenses that are subject to reporting requirement of 10 CFR Part 20, certain classes of licenses are required to provide NRC with an annual report of their workers' individual exposures. NRC in turn maintains such radiation exposure data in its radiation exposure information and reporting system. As a result, REIRS database represents a resource for use in responding to workers' requests for exposure information and dose history. One function of REIRS database is to provide individuals reports of radiation exposure monitoring data that licenses have reported to NRC. NRC under the Freedom of Information Act, the NRC must provide copies of whatever records that are maintained under this system. In addition, REIRS database represents a unique resource for use in satisfying 10 CFR, which requires that licenses must attempt to obtain records of prior exposures for workers who will require monitoring. How radiation workers and licenses can obtain those histories from NRC. Organizations and individuals may request those histories from REIRS and may submit requests for up to 10 individuals at a time. Requesters is required to enter his or name, title and contain contact information, and then identification number, name and birth date of monitored individual. Requester must also provide a password which will be needed to unlock those history report that an RC will send to requester upon submitting request form. Requester must also ask fax an organizational release form and signed by monitored individuals. Workers requesting their own histories should use individual's form. When an RC receives signed release form, agency creates requested cumulative occupational dose history for each identified individual and converts the report into Adobe Acrobat file. NRC then protects PDF file with the password and transmits it to requester. With regard to security, each step of process is specifically designed to protect sensitive identifying information. Once entered, this says that uses of security socket layers protocol to protect information as it's entered into form. Once entered, this information is processed, protected using password provided by requester and is encrypted for transmittal back to requester. So this is also gone. Now we'll see what can we take from this. Radiation exposure and cancer. It's very small, I can do this though. Radiation exposure and cancer. Associations between radiation exposure and cancer are mostly based on populations exposed to relatively high levels of ionizing radiation. Japanese atomic bomb survivors and recipients of selected diagnostic or therapeutic medical procedures. Cancers associated with high dose exposure include leukemia, breast, bladder, colon, liver, lung, esophagus, ovarian, multiple myeloma, and stomach cancers. Literature from US Department of Health and Human Services also suggests a possible association between ionizing radiation exposure and prostate, nasal cavity, sinus. Then again, these cancers that may develop as a result of radiation exposure are indistinguishable from those that occur naturally or as a result of exposure to other chemical carcinogens. Furthermore, literature from National Cancer Institute indicates that other chemical and physical hazards and lifestyle factors, namely smoking, alcohol consumption and diet, significantly contribute to many of these same diseases. Although radiation may cause cancer at high doses and high dose rates, public health data do not absolutely establish occurrence of cancer following exposure to low doses and dose rates. Below about 10,000 mrem, 100 msv studies of occupational workers who are chronically exposed to low levels of radiation above normal background have shown no adverse biological effects. Even so, radiation protein community conservatively assumes that amount of radiation may pose some risk of causing cancer and hereditary effect, and that risk is higher for higher radiation exposures. A linear no threshold dose response relationship is used to describe relationship between radiation dose and occurrence of cancer. This dose responses a linear no threshold dose response relationship is used to describe relationship between radiation dose and occurrence of cancer. This dose response model suggests that increase in dose, no matter how small, results in an incremental increase in risk. US Nuclear Regulatory Commission accepts LNT hypothesis as a conservative model for estimating radiation risks. So this was our radiation issue. Now we'll see what we can see here in the next one. Well, I think we'll go back. It's already over, I think. I could not take up this. Let us do this. Since NRC government relation those units exposure, leave it now. I think I think we should take LinkedIn now here. And now what actually I wanted to share is that these operations, which are of course 7 pages, a scope is there now. The scope is very clear. Procedures are applied to activities involving use of radioactive isotopes for carrying out non-destructive testing, and purpose of this procedure is to provide instructions for controlling radiographic operations, requirements of project procedures, and safe practices also be complied with when performing radiographic operations. And in definitions are saying, as we discussed before, there's nothing much on that. And employer is project owner, radiography method of non-destructive testing used to ensure integrity of plant, equipment and welding standards. Classified worker is a competent worker who carries out tasks involving radioactive sources. It's classified worker in SIVERT. Symbol SV's International System of Units. Standard unit of radiation. Old is equal to 1 SIVERT equals 100 rain and is absorbed dose. Then derived unit it is of equivalent radiation dose, effective dose and committed dose. Quantities that are measured in SIVERTs and designed to represent stochastic biological effect of ionizing radiation. And 1 SV is equal to 1 J per kilogram. Radiation sources include X-rays, gamma sources such as iridium-192, erbium-1169, cobalt-60, and shall only be allowed on site with prior approval from EPC contractor, site manager, employer, and RPS is a radiation source, site is a radiation protein production supervisor. Same way this is, responsibilities we'll take up tomorrow. We'll take some time on this because now it's too late. I think we should put it off now because thank you very much. I think we'll continue with this type of work. We'll continue with this. I think we should not close it, right?